Manisha, hello,
Ma'am.
how are you?
Fine, ma'am.
Okay, did you go through the topic which we had covered in our last class?
Okay.
Did you understand?
Yes, ma'am.
Okay, today we will
But,
start.
anyway, those formulas only we are
Yes,
how can we use? I'm not understood.
how to use that probability theory in expert system?
Mm.
That one you did not understand. Okay, let
How
me
can we
explain.
use?
Hmm.
Mm.
How can we?
Use that formulas or anything in expert system? I'm not able to get that point.
Okay, very good question. I will explain you. What happens
Okay.
is you are developing an expert system which contains knowledge base. Knowledge base has an inference engine. Inference engine, uh, inference engine is a component of expert system that performs um, the derivation of new conclusions. Um, New conclusions are nothing but the new knowledge which we obtain through the knowledge base. Hence, inference refers to the process of searching through knowledge base and deriving new knowledge. How probability is used? The question then comes, uh, application of probability in an inference engine. What happens is, consider that our expert system is a um, some disease diagnostic system. Uh, for instance, if I provide that if a person who comes to the expert system with some symptoms or signs, uh, give the information that he has cold, he has sneezing, he has cough, and then what the expert system does is, with respect to probability theory, uh, it has probabilities assigned to every condition. While deriving the conclusion, it considers the probability. Um, for instance, cold, um, no, body pains, um, the sign of body pain, the sign of cough and sneezing and runny nose. These four symptoms uh, exist in a person, then that person is predicted to have cold with a probability of zero point 0.9. Why zero point 0.9? Because it is a high probability that that person is suffering from cold because of all these signs and symptoms. Uh, Another example where if we say that a person is sneezing, uh, however does not uh, show other symptoms, then the system yield a value of 0.3% of 0.3 or zero point 0.4 probability value for a person to have a cold. Do you understand? Are you getting here? What you have to do, you have to assign probability values, and then you have to take joint probability. If body pain into uh, sneezing into runny nose, into cough, This is a joint probability. When you multiply all these probabilities, you may get the cold probability to be zero point 0.9 or higher, 0.95. If you have sneezing and cold association, sneezing, if it occurs, then the cold probability is only 0.3. So, in that manner, uh, probability theory is used um, for the derivation of new knowledge in a inference engine. Next, going ahead, we'll look at Bayesian belief network. It is also a probability theory like Bayes theorem, which specify certain rules and inferences, joint probability, conditional probability, and other formulas. Bayesian belief network. It is also called as belief network or causal network or just Bayesian network. Is a measure of two or more. Uh, you know, it is also a probabilistic graphical modeling technique. Uh, the difference between Bayes theorem and this Bayesian network is Bayesian network shows the probabilities in a graph. Graphically, it shows. So it is a probabilistic graphical modeling technique used to compute uncertainties by using the concept of probability. Here we have a tree kind of structure where you have a root. From the root you have branches or the successes. Um, Further, those successes can have sub successes, which are the children of the successes of root, and so on. And it creates the structure, and from the structure it derives the probability values. The formal definition is Bayes belief network is defined as an acyclic directed graph which does not have any cycles, and it is a directed, shows the arrows, wherein the nodes of the graph represent evidence or hypothesis and arc connects two nodes uh, which represents dependence between them. And the terminology is, if there exists an arc from node x to node y, x is called a parent of y and y is called a child of x. Uh, Moving on with this, we can form a set of all the parent nodes for a particular node uh, represented in the form of parent underscore nodes of xi, where xi is the node, and this parent underscore nodes return all the parent nodes of that particular node xi. Bayesian network or belief networks um, typically uses joint probability for the computation of probability value for a node, and it can be dependent or independent. which is given as p of x1 x2 up to xn equal to p of xn given x1 x2 up to xn minus 1 into p of x1 x2 up to xn minus 1. This can you can also write in this manner. um, xn given what happens is, consider that this comment here, pen x, if you have a tree structure like this, where each node has children, and to compute the probability, what happens is, if you consider this to be x1 and x2 x3 x4 x5 x6 x7, suppose this last x7 is xn, so x n, um, this you can get this given this one x3, and you can get this given x1, so that is shown in this manner. Hence that formula can be written in a compact manner like this. It is product of I1 to n uh, probability of xi, a particular node, given parent nodes of xi. In this example, if you consider this example, further this has more. So what consider this node. For this node, what are the parent set? This one, this, and that. These three are the parent set of for this node. When you do multiplication of this one, and this one, you get the probability for a particular node, and we have to do it for all the nodes. I equal to 1 to n for every node in a tree. Then you get the probability value for all the nodes. And here belief network representation looks like this. These two are parents, and D is derived from two parents A and B, and C is derived only from A. So C and D are called as conditional nodes because uh, they have a sort of dependence on A and B. D has on A and B, and C has on A. Whereas A and B are unconditional nodes because A and B does not have any dependence on any other node. Let us consider an example. Suppose the given probabilities are these for A 0.3, B 0.6, C given A 0.4, C given not A 0.2, and so on. These probability values represent the complete Bayesian belief network, They can also be expressed in the form of conditional probability table as given in 9.2. In 9.2, P of A is 0.3 and P of B is 0.6. These two are independent, unconditional nodes. P of C, we know that C is dependent on A. A is the parent of C. We get here two cases, C given A and C given not A. The regular case and its negation. Here for true, P of C given A, true. P of C given not A means false. P of D requires four combinations: A B, A not B, not A B, and not A not B. So true true means A B, true false A not B, and not A B, and not A not B. Those probability values are given. And we know that for four variables we can compute for A, B, C, D. D given A, B, C into C given A, B, and B given A and A. This can be simplified and it can be written as D given AB, because D is dependent only on AB, and C given A, and these two are unconditional. These two are conditional. And we know from that table uh, the probability for this is 0.7 into 0.4, 0.6 and 0.3. We get for ABCD joint probability as this. What is the advantage of doing this using belief network? If there is no belief network, what happens is you need to do for every combination, for every joint probability uh, value. However, all are not required as shown in this figure. All are not dependent on the other all. D on AB and C on A and AB are not at all dependent. Therefore, I'll get back to you. Okay, Manisha. So what we are doing is we are simplifying. Because of Bayesian network, uh, we need not generate unnecessary irrelevant combinations for joint probability. We are simplifying it and generating only those joint probabilities which are required and which are shown in our network. Okay, I hope that it is clear. Next, we'll look at how to make inference using a Bayesian network. The primary purpose of studying all these concepts are to uh, um, use them in an inference engine of an expert system, so that this mechanism of deriving new knowledge or conclusion uh, is simplified and it is made easy. Look at this question. What is the likelihood or probability that a hypothesis is A given C? How it is represented? It is represented as P of A given C, and it is calculated using the conditional probability formula and summing over all the variables in the network. In this network, there are four variables A, B, C, and D, and this can be written as P of A given C is equals to P of AC by P of C, because C is a child of A, and AC, P of AC can be written as a summation over BD for all these variables, and C is summation over ABD. When you use AC, what is left is BD. So BD combination, true false, B not B, D not D. If you take sum of all those probabilities, then you can find the probability of this. And for C, except C, we have three other variables in our network A, B, D, and their combinations will be true and false. So actually you have to do the summation of all that to obtain that, uh, and therefore in place of P of A comma C, this is put, and P of C, this is put because of this. And we can compute the values of numerator and denominator as A B C D plus A not B C D, A B C not D, A not B C not D. This is, look at here, B D true false, B true B false. This is B true B false. This is D true and D false, and this is B true B false. AC will remain same, and then we have will take on true and false combinations. So 3 1 2 3. So how many combinations you get? 8. Here you have 2, so you get 4 combinations. Here you got 4. Here you got 8. 1 2 3 4 5 6 8. And then when you write the values for every component, D given AB into C given A, B and A, and here D given A not B. Look at here, B not B and D not D. This is only for numerator. When you are substituting the actual values, probability values, you get these final values. Then the value of numerator which you obtain is this. And for denominator, you get different combinations where you should have A, um, not A, B, D, not A, not B, D, not A, B, not D, not A, not B, not D. C is constant here. When you substitute values, you get this, and when you take summation over all these values, you get P, probability of A given C is 0.33. How you obtained this? Again, let us go back. What is the likelihood or probability that a hypothesis is A given C? Given C means we discussed an example. If a student is regular, he pass exam with distinction. What is the likelihood or probability that hypothesis is A? What is hypothesis? Hypothesis is student pass exam with distinction. What is the condition given? Condition given is student is regular. So what is the probability? To find that probability, what we are doing? We are doing all these combinations in the form of our network, Bayesian network values, and substituting all the probability values to obtain the final result as 0.33. Like this we have to do for every query in that comes to the inference engine. That is the application of this belief network or Bayesian network. Another example of Bayesian network is you consider an alarm system installed in a house that can be triggered by three events, namely earthquake, burglary, tornado. So if a thief arrives, there will be a burglary, and a tornado storm can occur, and earthquake can also occur. So in any of the three events, the alarm system is triggered. So that how do you represent in the form of a Bayesian network? Alarm of triggering of alarm is dependent on earthquake, or it can occur when a tornado occurs. There is a spelling mistake here. And also when there is a burglary. So in any of the three conditions, this hypothesis occurs. These are the conditions. Uh, Again, there is a dependence between earthquake and tornado, because when a tornado occurs, there is a high probability that earthquake also occurs. That is a belief network. What you have to do in this belief network is you have to list out the probabilities. P of E, P of B. P of E is earthquake. P of D is tornado. P of B is burglary. P of A is alarm. P of E, P of B, E and P of D. E is the event. Event for this event, true, what is the probability? For false, what is the probability? A depends on three conditions. So you have to consider all the combinations for these three events for this alarm to be triggered. All the three true, what is the probability that alarm is triggered? These two are true and this is false, what is the probability? Likewise, you check for all the combinations. For three variables, you get 8 combinations. And for this one, for D, it's only about E. For D, if earthquake occur, tornado occurs. If earthquake doesn't occur, tornado, what is the probability that tornado occurs? What happens is when earthquake occurs also, there will be a motion in the ocean. and then that water may flow into, so that storm, like a storm kind of tornado will occur. So if earthquake occurs, what is the probability of tornado to occur? If earthquake does not occur, what is the, because this is dependent only on E, event E. So only two combinations you get. A is A is conditioned on E, B and D. E is earthquake, B is burglary, and D is tornado. D, tornado, is conditioned only on earthquake. Earthquake and burglary are independent. So all values you put in the equation to get the joint probability for all the cases. Now, how to do the inference? What is the probability that it is an earthquake given the alarm is ringing? So you have to find P of E given A. And what is the probability of burglary given alarm is ringing? So B, burglary given A. What is the probability of the alarm ringing if both earthquake and burglary occur? Means alarm ringing given earthquake and burglary. Like that you have different queries. So how can you find that? Uh, you can find that by using uh, the example that we discussed earlier. You have to uh, substitute different values and then to arrive at the probability of happening that particular event given the condition. uh, Next one is structure learning. Structure learning is, um, it is used in the process of inference. When the process of defining the network is too complex for experts, in such cases network structure and parameter or the local distributions may have to be learned from the data. Learning the structure of a Bayesian network is a challenging problem in the area of machine learning because most of the time it is not very straightforward to come up with the Bayesian network given the entire scenario. In this section, various methods are listed to come up with a structure. So one such method is optimization based search method, where you assign a score function uh, and then you try to find the uh, posterior probability of the structure given the training data. When the training data is given, you can create the structure by uh, assigning some kind of optimization based search method, some kind of scoring function. If you remember, we did heuristic search A star in a similar manner. That is one alternative to get to the structure or network when it is not very straightforward to directly draw the network. What are the advantages of Bayesian belief network? That this model encodes dependency among all variables, so it is easy to handle situation where some data are missing. You have the structure, and so it is easy to derive new conclusions and easy to handle situations where when any one of the data is missing, other you can make use of other data. And it is obviously very intuitive and straightforward for a human to understand the direct dependencies given in a network in a graphical like structure. And also the causal relationship can be easy to learn given the problem domain. Problem from the problem domain, you can know that what event is causing the other events. So that is called as causal relationship. And it is an ideal representation for combining prior knowledge and the causal and probabilistic semantics, because you know which variable is dependent on which other variable. You know about the parent and child relationship in a graphical representation, and thus it becomes easy for combining that. Bayesian statistical methods are used in combination with Bayesian networks to offer efficient and principled approach for avoiding overfitting of data. Bayesian there are some Bayesian statistical methods that you can combine with Bayesian network and to find the data which is not leading to overfitting. And there are certain disadvantages that probabilities describe single numeric point value, because uh, there is a distortion of the precision that is actually available for supporting evidence. You are not trying to find the joint probabilities of every combination, rather you are doing only for a few, and some kind of distortion might happen. And ignorance and uncertainty, there is no way to differentiate what is ignorance and what is uncertainty. Ignorance is not knowing anything about that. Uncertainty is you know something but you are not very sure. In Bayesian network there is no way to differentiate between the two. And computational difficulty of exploring previously unknown network is very high, as you know that in Bayesian network the starting step to uh, inference is to obtain the belief network, and it is not very straightforward to arrive to the network. And all branches must be calculated to find the probability of any branch of the network, even though the resulting ability to describe the network can be performed in linear time. This process of network discovery is a NP hard task. What happens is if there are uh, exponential number of branches, if there are many branches, you have to calculate the probability at every branch, uh, so it becomes a NP hard problem. And the quality and extent of prior beliefs are major shortcomings, because uh, mm, you know it is not very certain that that particular condition occurs with uh, the accurate prior probability. There is no accurate prior probability, and sometimes if you don't know about it, you just assume things. When you assume the things, it becomes a shortcoming. Reliability, reliability of Bayesian network entirely depends on reliability of prior knowledge in the form of your graphical network structure. If graphical network structure is accurate, precise, and incorporate all the dependencies with prior probabilities that are very known, then the whole Bayesian network yields accurate and reliable results. However, if the network is not reliable, then the result is also not very reliable. This is about Bayesian network. Tomorrow we will look at certainty factor theory. Okay, there is one more disadvantage. Selecting the proper distribution model to describe the data has effect on the quality of network, and therefore selection of statistical distribution is significant too. So it says that Bayesian statistical model in conjunction with Bayesian network performs better than only coming up with a network without any statistical distribution. Okay, tomorrow we'll look at certainty factor theory. I hope that today's class is clear. Okay, Manisha. Bye. See you tomorrow.